All right, people, let's talk exponent rules here. So let's start out up here in the introduction section. It says to express 7 squared times 7 to the third using exponents. Why do we need exponents? It's a nice, concise way to express really big or really small numbers. And it helps us understand numbers in terms of powers, in terms of repeated multiplication. And so that's kind of the idea behind it. Exponents are used in lots of ways in math and then outside of math as well. So here we go. 7 squared times 7 to the third is the first problem. If I was to expand that out, it would be 7 squared, which is 7 times 7 to the third, which is 7 times 7 times 7. All right, well, how many 7s did I multiply right there? 5 of them. So that, what I just wrote, is the same as 7 to the 5th power. So 7 squared times 7 to the third is 7 to the 5th power. Let's do the same here for 3 to the first times 3 to the 5th. That's 3 times 3 times 3 times 3 times 3 times 3. Well, how many 3's is that? It's 6. Maybe you're seeing a pattern here. 3 to the first times 3 to the 5th equals 3 to the 6th. How do you get 6 from 1 and 5? Let's do one with x's. X to the 4th times x to the 6th. If I was to expand that out, there would be 4 x's and then 6 more, making 10 altogether. So x to the 10th power. In general, folks, your rule is a to the m times a to the n equals a to the m plus n. We added the powers together. We keep the base and add the exponents, or add the powers. That's the rule for multiplying exponents with like bases. Let's rifle through some examples here to get you a little bit further exposure to these properties. So if we had something like 5 squared times 5 to the 8th, it would be 5 to the 2 plus 8, which is 5 to the 10th power. Let's come down here. 3 to the 10th times 3 to the 2nd. Keep the base, 3, add the powers, 12. What about a to the 4th times a to the 1st? That's a to the 5th. Let's go down to this problem right here. Does 7 to the 8th times 7 to the 2nd equal 7 to the 5th times 7 to the 5th? Well, this part of it right here would be 7 to the 8 plus 2, which is 10. And then on the right side of the equal sign, 7 to the 5 plus 5, also 10. So yes, they are equal. Let's do this problem right here. Circle all the expressions that are equivalent to 5 to the 10th. Let's go one by one. 5 squared times 5 to the 5th, that is 5 to the 7th, so no. What about 5 squared? Does that equal 5 to the 10th? No. What about 5 times 5 to the 3rd times 5 to the 6th? This is like 5 to the 1st, 5 to the 3rd, 5 to the 6th. You add the powers together, you would get 10. This one works. What about the next one? 5 to the 5th, 5 to the 2nd, 5 to the 3rd. Add those all together. Add the powers together, you get 5 to the 10th. Good. 5 to the 3rd times 5 to the 7th is 5 to the 10th. 3 plus 7 is 10. What about 5 to the 1st times 5 to the 9th? Add the powers, you get 5 to the 10th. That one's good. What about 5 to the 20th times 5 to the negative 2nd? Yes, you could have negative powers. That happens. Keep the base, add the powers. 20 plus a negative 2 is 18, which does not equal 5 to the 10th power. Let's go on to part 2 here. Notice the difference between this problem and the problems we've been doing. Now, please note that 6 to the 5th power raised to the 3rd is not the same as 6 to the 5th times 6 to the 3rd. These are saying two different things. Think about what this is saying. 6 to the 5th cubed. That means that 6 to the 5th is being multiplied by itself 3 times. So in other words, it's like 6 to the 5th times 6 to the 5th times 6 to the 5th. If I expanded all those 6's out, how many would there be? Well, think about the multiplication rule we just learned. Keep the base, add the powers. 5 plus 5 plus 5 is 15. So 6 to the 15th power would be your answer. How do you get 15 from 5 and 3? If you were to go back to the original problem, how could you get there without having to expand it out? 5 and 3, what can you do with those to make 15? Keep thinking about that. What about y squared to the 5th power? That's like y squared times y squared times y squared times y squared times y squared. All right, so think back to your multiplication rule. Keep the base, add the powers. That's y to the 10th. How do you get 10 from 2 and 5? Think about that. This leads us to our rule. So if we have a to the m raised to the n, the property would tell us that to simplify that, we would have to do a to the m times n. If you think back to the examples, we had to multiply to get the new power. So when you have a power raised to a power, keep the base and multiply exponents. Let's do some examples. 10 to the third squared. That's 10 to the 3 times 2, which is 6. 9 to the third raised to the fourth. That's 9 to the 12th. A to the fifth raised to the sixth. That's a to the 5 times 6, which is 30. Let's take a look at these problems right here. 5 to the second raised to what power would equal 3 to the 12th? So consider 2 times what would give me 12. Power raised to a power I multiply. 2 times 6 would give me 12, so I would need a 6 there. What about the next one? 4 to the blank raised to the fifth equals 4 to the 15th. What times 5 gives me 15? 3. So that would have to be 3. Let's go down to part 3. All right, so now we have C's and D's. Okay, we got a little bit more going on here. So I'm going to zoom in on this problem for a second. I want you to note that the second power right here is distributed to the C and the D. So it's almost like two little problems. It's like C to the second raised to the second and D to the third raised to the second. So C to the 2 times 2 is C to the fourth. D to the 3 times 2 is D to the sixth. That would be your answer. Let's go over here. Maybe pause the video for a second, see if you can do this one by yourself on a piece of paper, and then resume to check your answer. What you would get is m to the 2 times 3 is 6, and n to the 4 times 3, which is 12. Last couple examples here. I just want to show you one like this one right here where you have integer bases, 2 different integer bases with 2 different powers, but your strategy and the way you go about it is no different than what we just discussed. So that third power that's outside gets applied to there and it gets applied there. So it's 4 to the 3 raised to the third. 3 times 3 is 9. 5 to the 2 times 3, which is 6. Okay, so that's how you would do one like that. No different than the previous examples. That third power outside gets applied to each term inside the parentheses. One more problem for you. This is a bit of a challenge question. I'll just write it out right here. What if I said 3x to the second raised to the third power? So the difference here is we've done this. We've done x squared raised to the third. We're comfortable with that. I think hopefully at this point we know that's going to be x to the sixth, 2 times 3. But what do we do with this 3 right here? This is really like a 3 to the first. So similar to this example over here, how we applied the third power to the 3 and the 2, that third power over here applies here and it applies here. So really, the new coefficient is 3 to the 1 times 3 power. So that's 3 to the third power, which is 27. So your answer would be 27x to the 6th power. There is something like this on your progress check, so I wanted to show you an example of that. I'll do one more of those. All right, so I'll just write it over here to the right here. So what if I had 2x to the 6th raised to the third? So this is like 2 to the first power. Maybe pause the video, see if you can do this by yourself, and then check back in. This would be 2 to the 1 times 3, which is 3, and x to the 6 times 3, which is 18. So simplifying that, 2 to the third power is 8, and then x to the 18th. That would be your answer for that one. All right, that is it for the mini lesson today. Check out the practice problems that I provide on Edulastic, and then there's a short progress check to try out as well. The blank copy to these notes and the key is also available if you want to scroll through and take a look at some more examples or do some more practice. All right, be well. Talk to you soon.